Hello everyone, I'm Shadab Anjan. And the topic of our presentation is covariance of electrodynamics, which is basically the invariance of Maxwell's equations and the laws of electrodynamics as we change frames, inertial frames. So according to the first postulate of relativity, according to Einstein, for different inertial frames, you cannot tell which one is we cannot tell about the inertial frames because all the laws of the physics are same, like all the laws of nature, they are same in all the inertial frames. So basically, we are trying to form a formulation of the electrodynamics in inertial frames such that they are consistent with the transformation. So we're trying to find the Lorentz and other transformations for various terms that come into electrodynamics. So we start with the Lorentz transformation, which is basically the Lorentz transformation is just like if you have two inertial frames k and k prime, in which k prime is translating with respect to k with a certain velocity v, the position, the coordinates of a certain event are related as this, where x naught prime is the ct, x naught is ct, and x are the various coordinates. Beta is v over c velocity, and v is in some arbitrary direction, but they are translating. So the axes are parallel, and these will use the analogy, will drive the analogy from these to form the concept for four vectors, like any quantity which transforms like this into like when we are moving, when we are observing from two different inertial frames which are moving with respect to each other, and they change like this, they're called four vectors, and the components are related like this. This is the only criteria. So what we see for like there is a quantity that's always conserved for a four vector. Here it's like ds square, which is s square, you can say ct square minus the sum of squared sum of all the coordinates. Similarly, for four vectors, we have this quantity as a conserved quantity, which the proof is being given like this. A naught prime, since it is a four vector, transforms like this. B transforms like this, and you just calculate the left hand side and show that it's same as the right hand side. So doing the calculation, we see that a naught prime times b naught prime is gamma square, like a naught gamma square, and all the four terms, one having beta square, one having beta, yeah. And similarly, a prime dot b prime is the dot product, like just multiply a parallel prime by b parallel prime and take dot product of a perpendicular prime and b perpendicular prime, because in two directions. So we get a prime, this quantity, we subtract the two to get that gamma square a naught b naught minus this whole thing. We take a naught b naught minus a parallel b parallel common. This comes out to 1 minus beta square times a naught b naught minus a prime b prime, and 1 minus beta square is nothing but 1 over gamma square. So we get a naught prime b naught prime minus a prime b prime to be equal to a naught b naught minus a parallel b parallel minus, so this quantity is just a dot b, like this is a naught b naught, this is a vector 3 vector, b 3 vector dotted. So this is same. Now tensors, now we'll talk about tensors in space time. So tensors are very important concepts. So consider that there is like these are the coordinates, and then you transform and go to some other like other frame, and this is a transformation equation. So anything that transforms in the same manner as these vectors, like these coordinates do, is called a co-vector, like the grads of these coordinates. And something that transforms in a different manner that we'll see for rank 1 we're talking about, it's called a contravariant vector. For rank 0 tensor is just Lorentz invariant quantity, and rank 2 tensor we'll talk about. We'll have metric tensor and other tensors of rank 2. So that's the thing. Okay, so this is a transformation equation for a contravariant vector. Like if you want to calculate a certain index component of that contravariant vector, just do a summation. This is summation, so dou x beta or a beta. That just means you start, like, let's say this is 2, so you write dou x2 prime, and you take the summation with x1 x2, like it's written here. Yeah, so this whole thing is expanded form. However, a covariant vector transforms differently like this. It's like basically dou x beta over x dou x alpha prime. The inverse of the differentiation that we were doing there. And the various transformation between like a second rank tensor has been given to convert a contravariant tensor under the same rule of transformations. You use this. And for covariant, you just use two covariant definitions, and for a mixed, use this, where this is the summation that like anything that appears twice will be summed together, like dou x alpha prime over dou x gamma f gamma delta. So this will run over gamma equals 1 to 4. Similarly, dou x prime beta over dou x delta, this will run from get delta 1 to 4 summation. Same will be followed. Whenever it comes twice, it will be summed over all the values that variable can take. So what the dot product is defined as this, between a covariant and a contravariant vector. And we see that this is a invariant quantity, and this can be easily proved like this. Just take the how b, like just take the transformation like b prime a prime b prime dot a prime, which is nothing but transform b. Like this is the formula, and this is the formula for b beta a gamma. Okay, like we'll just show that this is same as b alpha a alpha is same as b prime dot a prime. And we just do this. We just see that if this quantity dou x beta over dou x gamma, if beta is not equal to gamma, they are independent by considering, so this will be 0. So this is non-zero only if they are equal. So Dirac delta, so a Kronecker delta function, and this comes out to be beta equals gamma. So b beta a beta summation or b gamma a gamma summation, which is same as this is what we are doing, the same dot product. Now this is like we know that this is a Lorentz invariant quantity. The various coordinates and time, the cdt square minus dx square minus dy square minus dc square. And what we come to know about is that we have a special kind of a tensor which can convert between like we say this is a this is called a metric tensor that we'll be using to convert, like to change the indices of various covectors and contravectors and and like matrices, covariant matrix, covariant tensor and contravariant tensor. So we have this by definition, like for a flat space time, we know that the contravariant and covariant are same, and they have like the first term, the first diagonal is 1 and others are -1. And yeah, and this is a transformation equation between a covariant and a contravariant vector. And g alpha beta, each of the coordinates, just sum over g alpha beta matrix multiplication. Just take this and just the vector A. Yeah, and this matrix actually used to change the indexes like upper to lower, whatever you want to. Yeah, and like this is simple. You see that if this is if these are the components of a contravariant 4 vector, you multiply it, try to change into a covariant 4 vector. You see that by multiplying this whole vector through this metric tensor, you get that the 3 diagonal terms make these negative, and this remains same because of 1, which is trivial to see that the 4 vector obtained in the covariant form is just a naught minus a. These are components. This is just to denote that these are same. Yeah, and the scalar product of 4 vectors was defined earlier as b alpha a alpha, which so like each one to be a naught like this. I'm sorry, this is a dot a. B dot a is b alpha a alpha, so b naught a naught. And since you know that this b alpha is negative of b alpha a alpha, right? So yeah, so like you'll apply the metric tensor. So writing in this form as a component of a contravariant vector, you'll say that b upper index 1 is negative of the b lower, like the component. So you use that to convert it, and you write the components. You get the components as minus b dot a. minus b1a1, b2a2, b3a3. Negative because of the metric tensor. And now we're trying to find the matrix representation of the Lorentz transformations. So by simple chain rule, you see that the partial derivative with respect to a component, like partial derivative with respect to alpha prime, is that you first take the partial derivative with respect to x beta, and you take then the derivative of x beta with respect to x alpha prime. This is simple chain rule. And you see that if you consider this as two different quantities, these are the conversion factor is same as that between two um, between covariant vectors. You see x beta over x alpha prime, like it's not x alpha prime over x beta. So these two are like covariant quantities. And the partial derivative, like sorry, partial derivative with respect to four vectors is defined in this sense. Take the partial derivative with respect to each of them. Del is simply dou over dou x1, dou x2, dou x3. The covariant form for this with respect to covariant components is just dou over dou x0. This term is same. These terms are just negative because of the metric tensor conversion. So the derivative will also be like the negative will come out, and this will be a negative gradient. The four divergence is defined as this dou alpha a alpha, which is very simply comes out to be this, because you're taking, it's simple, like, yeah. And this thing, if you take x0 in the general sense, in space and time, this is ct square, like ct, and this is the like, if yeah, dou alpha is like dou over dou ct, dou over dou ct, or 1 by c square dou square over dou t2 minus grad square with respect to x y c, which is same like, which is the normal wave function equation. Like grad square psi is minus like, plus 1 by c square dou square dou t2 is 0. So this was the introduction part, and I'll do the tutorial problem. The tutorial problem. Yeah, so the tutorial problem is that we have a point particle with charge small q, which moves, which has placed an electric field E, which is in the z direction, and the initial energy and momentum of the particle is in along the y direction, that is u naught. We have to find the trajectory for the particle. So, and we have to show that it's equal to this cos hyperbolic thing. And the momentum, in relativistic cases, we know as gamma mu. Gamma is the same as what we are doing, like 1 over 1 minus beta square root over. So we are using dp over dt is dp over dt is the dp over dt is dou square x over dou t2. dp is force m times. So we are using this, will be always there, because the charge will accelerate in z, we make it accelerate in z direction, and this will be always be there, the component of velocity or momentum. So we just integrate to get this form of equation. Just integrate instantaneous velocity. You have the velocity, you get dx over dt, and this integrate to get dr over dt. So in each of the coordinates along z and y hat, we get the integral to be this, and using the property of sine hyperbolic function, we get like, considering it started from origin at t equals 0, we get this same trajectory as it was. Yeah, thank you. This was all that I had to present. Stop share.
Final take. Hello, I'm Yare and I'll be demonstrating the covariance of electrodynamics. First, before we begin, uh, we want to know what we are actually trying to do. Basically, to show the covariance of electrodynamics, we want to write the Maxwell's equation of motion in terms of in its covariant form. So that would involve writing it in terms of proper time and the four vectors and tensors. So in order to do that, we must identify what are the four vectors and tensors in our equation of motion. So we begin by considering a charge. and left hand side is basically the 4 force vector, and P alpha is the 4 momentum vector. This is basically mass times the 4 velocity vector. And by basic algebra, we write this in terms of the proper time, and we get this. After this, we get after this you want to derive the 4 we want to derive the time part of the uh, 4 force vector. So we do that again by some simple algebra. You can check it in the report. Right, I won't be going through it because I only 15 minutes. uh, we get dp naught by d tau s q by c u dot e. So if we know that the left hand side is the 4 force vector, and that if we know that q is invariant under Lorentz transformation, which is proved experimentally, we can show that uh, electric field the electric field in this case, the components of electric field in this case is basically the first first row of a second rank tensor. So this tensor is very important in showing the covariance of electrodynamics, and we will be showing it, and we will be finding what this tensor actually is. So starting with the microscopic Maxwell equation, which basically means ignoring d and h, we have the continuity equation, and comparing with the 4 divergence of 4 vectors, this thing, we naturally postulate that rho and j form a 4 vector, with j alpha being this and del alpha j alpha being this. Okay. So next we consider a small charge element in a volume d cube, and we say that the density of the charge in the volume d cube is rho. We know that the charge does not change in the Lorentz transformation, so we know rho prime d cube x prime is equal to rho d cube x. But we know that 4D volume element is basically invariant. So I mean we can show that basically by doing this Jacobian thing, and yeah, so which that suggests that x naught is basically equal to ct. Sorry, x naught is equal to ct. That suggests that the time part of this j alpha, then c rho behaves the time component of this j alpha 4 vector. Okay. And using Lorentz gauge condition, we can basically show this, which we have done multiple times in class. And with Lorentz condition, this. Now again, if we compare this thing to our 4D divergence, we can postulate that A alpha is a 4 vector, with the temporal part of the 4 vector being phi. If we consider this to be the 4 vector, our equation basically becomes this thing, where this is a D'Alembert operator. The box operator is basically this. Uh, so this and this is just the Lorentz gauge condition. This thing. Now from the Maxwell equation, we know that E is equal to minus 1 by c dA by dou A by dou t minus gradient of psi. Again, now we see that the x component of Ex can be written as minus, if we consider the 4 vector that we defined earlier, the x component of electric field can be written as this, and x component of magnetic field can also be written like this. So now we define our f alpha beta, our f tensor, which is basically this thing, and from this equation we conclude that f alpha beta in its matrix form will be this. So we know each component of f alpha beta. Also, just for the reference, we show that the covariant form of f alpha beta is just, we get the covariant form of f alpha beta by just substituting e with minus e. Now we define one more quantity called the fourth rank tensor, and this is the properties of the fourth rank tensor. And using that fourth rank tensor and our f alpha beta tensor, we define one more tensor called dual field strength tensor, which is basically this. Now we know this from electrodynamics. These equations are from electrodynamics. Basically, in order to, like I said earlier, in order to show the covariance of electrodynamics, we would like to write the Maxwell's equation in its four vector form. So that's what we are doing here. Now again, if we consider our tensor f alpha beta, then these equation can be written like this. So this is basically the electric field part of our Maxwell's equation, and the magnetic field part, the homogeneous part, can be written like this. Now again we substitute this curvy f alpha beta as this thing, and then we can write this entire thing as this. So basically, with the four vectors that we have obtained, that we have postulated, j alpha, a alpha, and f alpha beta, we can write the Maxwell's equation in its covariant form. That basically shows that the electromagnetism is covariant. The Maxwell's equation are covariant. Now, just for completeness, I'll show you how that f alpha beta was related to dp alpha by d tau. So yeah, we know that dp alpha by d tau is equal to m du alpha by d tau, right? It comes from the definition of p alpha, the p4 vector, and d yeah, and du alpha by d tau. We know that this thing is is essentially equal to f alpha beta u beta. So that's how we know that f alpha beta is a tensor here. Okay. So going from microscopic Maxwell equation to macroscopic Maxwell equation is just as simple as replacing the electric field vector E by D and D by H. Let me explain this part again properly, because I think I have not explained it properly. So um, we know that dp by d tau is equal to this thing, and we know that dp naught by d tau is equal to this thing. So if we just write these equations in terms of like each particular component, we will see that this is true. So like we expand p alpha, so p vector in terms of p1, p2, p3, and e in terms of e1 and p3, and this the dot product this, sorry, cross product this, and we find the components, and we will essentially get this thing, p dp alpha by d tau is equal to this thing. But we know that p alpha is equal to mu alpha, and when we differentiate it, we get du alpha by d tau. So yeah, finally the covariant form of Maxwell equation in macroscopic state is this. Here we just replace f of alpha beta by g of alpha beta. In f, it's the exact same tensor. So exact same tensor is this one. It's not exact same, I mean it is same, but the only difference is instead of e we have D here, and in terms of B, we have H here. So that's how we get the macroscopic covariant form of Maxwell equation. Thank you.
Hello, I'm Aldo Mondal and we are group number 6 and our topic is covariance of electrodynamics and I'm going to present the transformation of electromagnetic fields with respect to the covariance. So we have already seen that the electric field E and the magnetic field B are the components of the second rank tensor f of alpha beta, which is basically the contravariant form, and we have the components of the electric and magnetic field as a as the uh, components of the second rank tensor electromagnetic field tensor. So this is in accordance with Jackson's Gaussian units. If we are supposed to use SI units, then the electric field components are supposed to be divided by the factor of c, which is basically the speed of light. So if we want to convert f of alpha beta from one inertial frame k to another inertial frame k prime, we are supposed to contract its indices with the transformation tensors, which is basically f prime of alpha beta, which is in the prime coordinate system, and which is basically delta x in alpha by del of x gamma into del of x prime beta by del of x delta into f of gamma delta, which is basically the field tensor in the unprime coordinate system, and gamma delta are basically the repeated summation indices. So we can try to represent the following in the matrix form as well. So we can see that the boost matrix A for this transformation is basically a linear transformation, and we can write A alpha subscript gamma as del of x prime alpha by del of x gamma. So if we expand in terms of the matrix form, we can write f prime of alpha beta equal to A alpha subscript gamma into f of gamma delta, which is basically the field tensor in the prime coordinate system, into A beta times delta. And we can write the contravariant form as well. So if we use the compressed notation for this, we get f prime equal to AF A prime. So for the specific Lorentz transformation, we can consider a boost along the x1 axis only for simplicity, of course. It can be in any particular axis in general, uh, but without any loss of generality, we would like to choose a boost along the x1 axis only, and it's also in accordance with Jackson. So let's say that the boost is along the x1 direction with speed c beta. So we have a boost matrix A as basically it's the top, the left 2 into 2 matrix is basically having the diagonal terms as gamma and the off diagonal terms as minus gamma beta, and the bottom right 2 into 2 diagonal is the identity matrix. So using the above formalism, we can easily write the primed components in terms of the unprimed components. So we see that f prime of 0 1, so 0 1 is basically the first component or second component in this. So f prime means the prime coordinate system. So it would basically be minus ex, as we can see, and it's minus e1 prime. 1, 1, 2, and 3, like here in this case, e1, e2, or what would be what we would see later, that if b2, b3, these have nothing to do with the contravariant indices. These are just the original, like the ordinary Cartesian components. So we basically ex, ey, or ez. So we have nothing to do with the contravariant indices in this case. They are basically just the Cartesian components. So we see that f prime of 0 1 can be represented in terms of the AFA prime compressed notation as A0 subscript 0 F01, which is basically the first component E1 of the unprimed coordinate system for the electromagnetic field tensor into A11 plus A01 F10 into A11. So when we see that it's equal to minus gamma square E1 and minus gamma square beta square E1. So we there is a very fundamental result that we know that in gamma square plus gamma square beta square is basically 1. So we get that E1 prime equal to E1. So this is one of the components that we have worked out from Jackson, and using the similar boost matrix and the result that we have already obtained for presenting f prime of alpha beta in terms of the unprimed field tensor, we can obtain the explicit transformation equations for all of the components of the electric and magnetic fields. So we uh, uh, get the following equations. So E1 prime equal to E1, which we have worked out. We can work out E2 prime to get gamma E2 in minus gamma beta B3. E1 and E3 prime is basically gamma into E3 plus beta into B2. Again, we get, so it's going to be E3 prime. Here, a very trivial mistake. So it's going to be E3 prime. And again, we see that B1 prime is basically unchanged. It's equal to B1. B2 prime is again a mixture of B2 and E3, and B3 prime is a mixture of B3 and E2. So we notice that the components in the direction of boost remain unchanged, and this is quite obvious and very intuitive. We have already seen that the components of velocity or even coordinates don't change in the direction of the boost. The perpendicular components are mixed by the boost. As we can see, they are a mixture of electric and magnetic fields for each individual case. And we can always get the inverse relations for the transformation equations by exchanging the unprimed and primed coordinates and replacing beta with minus beta. So if we try to generalize our argument for relative velocity v in any arbitrary direction between the two coordinate frames, then the transformation of the fields can be written as E prime equal to gamma into E plus beta cross b minus gamma square by gamma plus 1 beta into cross dot product between b and beta and e. Now this is a relation which is quite intuitive. We have come across the factor gamma square by gamma plus 1 even in while representing x prime in terms of x or even v prime in terms of v. So this is something that we don't know. This is something that we know already, and we are just seeing this factor appear again in terms in for the transformation of the field. We can say similarly for b prime that it's equal to gamma into b minus beta cross e minus gamma square by gamma plus 1 into beta times beta, the dot product between beta and b. So we observe that E and B have no independent existence, and while generalizing the argument as well. So this means that a purely or electric or magnetic field in one coordinate frame will always appear as a mixture of electric and magnetic fields in another coordinate frame. So this also means that we can transform a purely electrostatic field into purely magnetostatic one, because we already have beta less than 1 as a constraint, and that always has to lead to a mixture of fields. So if we take a very basic example of the transformation of the electromagnetic fields, we can consider the field seen by an observer, say in the system K, when a point charge Q moves in a straight path with a velocity v. So with respect to the system K prime, we can say that the charge is at rest, and the transformation of the fields is thus given by the inverse transformation equations. This is because the charge is at rest with respect to the system K prime. So we can now suppose that the charge moves in the positive x1 direction, and that its closest distance of approach to the observer is b. So the observer is at the point P, and as we always have stated this, so at t equal to t prime equal to 0, the origins of the two systems coincide, and the charge q is at its closest distance to the observer. So in the frame K prime, the observer's point P, where the fields are to be evaluated, we want to evaluate the fields at that point. And it has coordinates which are very basic and which are elementary as well. So it's basically x1 prime equal to minus vt, x2 prime equal to b, which is the closest distance of approach, and x3 prime equal to 0 because we don't have any type of motion along the x3 direction. And the observer is at a distance r prime away from q, which is basically the square root of b square plus vt prime whole square. So as always, we would want to express r prime in terms of the coordinates which is in the frame K. So the only coordinate which is
Uh, Hello, my name is Mukesh. Now I'm presenting for the team 6. I'm presenting the topic relativistic equation of motion for spin in uniform or slowly varying external fields. Now, just let me go through the what are the sections in my topic. The first one is covariant equation of motion. It is for the spin, and the second section is at the end of the 6.1 we'll be having the equations for ds by d tau and d tau. And in that equation, we'll get the term for Thomas precision. And in the 6.2, we'll be rewriting those equations, in terms of the omega t, Thomas angular frequency, and we'll be seeing explicitly how they are connected. And in the last section, we'll be having the using the is an application of the 6.2 section. And now let me go through them briefly. So you can see that the first equation is the ds bar by here. S bar is the spin of my electron, and ds bar by dt and the rest prime is given by mu bar cross b dash b bar dash. Here my mu bar is my magnetic momentum vector, and my b bar is the magnetic induction. If the electron is placed in when the electron is placed in the external electric and magnetic field. And this b bar is given by here we have seen in the before section. The b bar is given by this equation. Now, and the mu bar is equal to g by 2 mc times s bar, where s bar is the spin of the electron, and here g is the lambda g factor. And we discussed these things in the previous section. And using these two equations, we have written final rate of change of the spin vector with respect in the rest frame. Now, uh, in the electron frame, the 4 vector of the spin angular momentum, if we take the time component, we take it as 0, and the space components is just the spin vector of the electron. And in any other frame than the electron frame, the time component of the spin 4 vector is not 0. So here we have an inertial frame k bar k, and another frame which is the k prime frame, in which the electron is there, and that k prime frame is moving with the velocity of v bar equal to c times beta bar. So if there is a frame k prime which is moving with a velocity of v bar equal to c beta bar, and we are writing the coordinates of the of a particle in that frame with respect to the inertial frame some k. And these are the transformation equations, where the first component is the time component and second is the spatial vector. So using these two equations, we have got the equations for the S small s bar equal to cap in terms of the capital S bar. Here, if you say observe, small s bar is the spin of the electron that is in the inertial frame of k prime, and here s bar is your readiness spin of the electron in the inertial frame k bar k. And if you look into here, like sorry, it's a mistake. Like here, s naught prime gamma should be like equal to s naught minus beta dot bar s bar equal to like 1 by c into u alpha by s alpha. We said that before that this s naught prime, it is the time component of the electron in its inertial frame. It should be 0. On applying that conditions, we get the orthogonality of the velocity 4 vector and the spin 4 vector, that is u alpha times s subscript alpha equal to 0. And the time component the inertia frame is given by s not equal b bar dot s bar, and using 6.1, yeah, using this equation, we are writing s bar yeah finally we are writing the s bar like using these equations, and we are writing capital S bar and also capital S naught. These are the four velocity components in the inertia frame K. So to get this, we will just use the inverse equation of this just by replacing minus beta bar by minus beta. Yeah, and now see if we consider the equation here, ds bar by data bar, like rate of change of spin. We are now trying to write the ds alpha by d tau, like in terms of the four vectors. So here we like the directional field be like f. We considered some 3-4 vectors. These are given by this, and now we are saying that your ds alpha by d tau can be written in terms of these four vectors, and the equation is given by this. And now we are applying the condition of 6.2. Yeah, on applying the condition of this is the condition orthogonality u alpha into s alpha equal to 0. We get this equation, and on using this condition for this equation, we get the final equation for this, and this is just a mathematical calculation, and we say that it should be 0, so that a1 equal to a2 and a3 should be -1. And in comparison with the equation of this, we are getting the component a1 equal to g by 2 mc, and we are writing ds alpha by d tau finally here. Now your du alpha by d tau is can be written by this equation. This is done in section 3 by my group mates. Then we are finally we are using this result for this equation, and we are writing ds alpha by d tau, and this final equation is called the BMT equation. Now in this equation, the last term is connected to the Thomas precision of spin. Now we are going to explain how it is that. Now this is a result s alpha into du s lambda into du lambda by d tau equal to minus gamma into s bar dot dv by d tau. Now we are trying to write ds bar by d tau again. So as you can see, like we are doing the we are here actually generalizing the equations. Here your ds alpha by d tau, it is the equation exponent is your invariant equation. Here we know that d tau is the proper time, and now we have this BMT equation, and wait, this is a special case of the of our BMT equation. It's only when when you can write du alpha by d tau equal to e by mc into f alpha beta into u beta. is when your electromagnetic fields are uniform in space, and you can like net these terms. And now take this BMT equation. In this equation, take this first term. And now I am saying that this for the terms of this first term forms a 4 vector, and we are representing that 4 vector by this f naught and capital F bar. And now we are substituting this result in the second term of this equation, and also using the fact that u alpha, your u alpha is gamma times v bar, and also you know that time component of the pole velocity is gamma times c. I'm substituting that and writing this as your for the space component we get ds bar by d tau equal to f bar plus gamma. This is the equation, and for the time component it is ds not by d tau. This is the equation. Now on combining these two equations uh, and also using this equation, yeah, s equal to s bar minus gamma by gamma plus beta thus equation. We are able to write another equation, new equation, that is ds bar by d tau equal to f bar minus something. So if you can observe here, here S is capitalized, that is the spin of the electron in its initial frame divided by d time, that is a proper time. And now we are substituting our Thomas precision frequency, that is omega tau bar, using this, and we are rewriting this above equation as this. And this for motion in electromagnetic fields, you have the result, this dB bar by dt equal to d bar by mc times e bar plus beta bar cross beta bar minus beta into beta bar dot e bar. And using the transformation properties of your magnetic field, beta prime equal to this one. This is done in the previous section, and we are rewriting this above equation in terms of f bar prime, and we get this. Now we are writing the ds bar by dt bar, the rate of change of spin vector in its reference frame, by using this equation on substituting here and on applying some algebra, and you get this equation, final equation. This is called the spin vector in Thomas. The motion for the spin vector, this equation is called as Thomas equation. Rate of change of longitudinal polarization. So your longitudinal polarization is defined as the rate of change of your spin vector parallel to your velocity. So you just take a d by dt of b bar hat dot s bar, where this is the unit vector in the direction of velocity, and you substitute ds bar by dt bar and db by dt bar from your above results, and you get this equation on algebra. Now this equation is very interesting. Why? Because if you consider only magnetic field region, there's no electric field. On taking g equal to 2, you get 1 minus 1 and it becomes 0. So your longitudinal polarization, whatever is the quantity, remains constant over time. And for the particles of relativistic particles for whom beta is very close to 1, like beta bar is very close to like 1, like beta is very 1, close to 1. On substituting, you can see that this value is close to 0. when you take G equal to 2. And even though there is your electric field, the change in your long-term polarization is very, very slow. And for electrons and other particles, similar particles, like your G is not exactly 2, there is some order of correction of alpha by pi. Uh, so because of your G minus 2 is very slow, the long-term polarization of beam of electrons changes very slowly by, because if you take here, like you can see that this value becomes small. And yeah, and there's another quantity which is defined as A equal to G minus 2 by 2, called as normally or anomalous magnetic moment. And for some of the particles, the muons, electrons, and uh, positive electrons, like the calculated values are this, and you can see that they are very small. And yeah, that's the end of the section. And next, my uh, teammate will explain the small tutorial problem. Okay, thank you.